He also told us that we were going to have a final calculations for our project, just the variations. That was split, but now that we said we're not going to do anything with this class, I think we got
Wait, a minute.
calendar year for one, but there's also looking at it, so we would have been able to by then. I guess that made it great. Project is like rented stuff. He also had a one-point do that with the final. The final would be directly linked with the but then it could install the one tree. Well, the only thing on the other one is that he said he's kind of like you go to insert, take the and just through all that to his project over the next release of the pressure.
All right. So, let me ask you one quick question before we start with this. How many of you have taken or have just researched a little bit about queuing theory? Operations research or something like that. Okay, so I'm going to go then with a very, very specific level of detail on this. So, queuing theory is very important because it provides the framework for explaining processes. As you saw, we were just measuring variation, but we need to understand how queues work. And it is highly utilized in industrial engineering to explain different algorithms, different methodologies of how to set up the processes. And it is important because of what we just covered. It is important because it focuses on the analysis of how the behavior of the queue happens under certain conditions that are determined by capacity, time, and the process that is functioning as a server. So basically what this is intended for is this explains a network, a more complicated system that has all that thing, that those relationships that we just saw, that is arrival, processing, departure, arrival, processing, departure. And the behavior of this, we just have touched the variation part, right? We have touched the variation part if we were to have available certain parameters such as time of arrival, time of processing, time of departure, right? And if we collect that through time, we can determine the coefficient of variation and so on. But this theory, queuing theory, tries to explain mathematically what is the probability of something to happen, and if it behaves in a certain manner, how are we going to set up these things so that it is efficient for the customers. Just for example, one of the setups that is very important through queuing theory that was analyzed and it was proven that it's more efficient is the example of movie tickets. For example, if you go to, what is this theater here in Farragut? Pinnacle, yeah. So to get your ticket, they have several windows, right? And then they set up something separate that is just like the curved line. And you find that anywhere now. But the way it used to be before, there was no line. You just line up in a window so that you get your ticket. So what happened, or what made this configuration to be more efficient than that old configuration of just lining up to the window that is available? Queuing theory. basically what happens is, I don't know how many windows are there. How many are usually there open? Like 5, 6? Something like that. If there's nobody there, the most natural thing for you to do is to go straight, just skip the whole thing. Well, if you're very proper on your behavior, you would go into the maze here and then go, but the most logical thing is you go straight to the window, right? When do you take the line? You take the line when there's people waiting, okay? So what happened in the past was there was a person in every window. What was the most natural thing to do? You line up where? 6 windows. The 6 windows are available. You line up behind the shortest line, okay? And that same thought was followed by the people that was arriving after you. If at any given window of time, we would measure the waiting time of the last person, let's say there's 100 people overall, the 5 windows that can line up, okay? And then we take the waiting time in line for the last person to arrive, okay? And then we cut off there, and we make an average of all people's waiting times, okay? If we compare that to the configuration of these same 100 people lining up in a single line and just getting dispatched to whatever window is available, the waiting time in average is much smaller than with the other configuration. So that's what queue in theory does. That's why the single line is more efficient because of one reason. Because as soon as a window becomes available, it creates that fairness policy of the next customer that arrived in time to be served, regardless of how long it's going to take at the window, because as soon as the next window becomes available, the other customer gets in. But if you line up, you may think like, how would that be possible, me being the 100th customer, to have a shorter waiting time if there's 99 people ahead of me, compared to, let's say, there's only 9 people ahead of me in that particular lane, or that particular window. How would that be possible? Something happened to that person there, and the policy here is you cannot change lanes once you line up to one. You line up there, something happened, you won't be able to get your tickets until the other 9 get their tickets, whatever time it takes for them, right? In this configuration, it doesn't matter. In the single line, bless you, doesn't matter, because as soon as another window becomes available, if some customer is having a problem and they take like 2 minutes, or the computer just messed up or whatever, it doesn't matter, because you can switch, and all the customers get served.
I mean, you're still going to have one teller at the movie theater that's slower than everybody else.
Mm-hmm.
But what you're describing allows the fastest one, or the fastest 2, to have a bigger impact on the total population.
Exactly. And possibly, if you measure that, the impact it's going to have over how many people they serve is going to be much higher than the rest. But that's coping with that variation. So there's many assumptions behind this, but again, it helps to diminish a little bit, or to try to create that buffer for that, the variation part, and to get the service level that the people is expecting. So that's the magic of queue in theory. So what do we got to know in order to establish the understanding of queues? What is a queue? A queue is...
Wait time.
Sorry?
Wait time.
Is an item waiting to be served, right? So we're gonna understand when that item arrived. That's important. How long did it take for that item to get to service and how long did it take that service, how many servers we're going to have. Okay, that's very important. And then if that queue has a limit. Okay, again, I mentioned earlier, there's going to be many cases where the queue has a limit. You go to the doctor, you made an appointment, but you realize that there's a lot of people waiting. You may decide to stay standing or leave. Okay, and that's a natural pattern. The physical space constrains a lot of times the capacity of the queue. And the reaction is people would leave, most likely. Some would decide to stay, but then from that capacity of the space, it doesn't vary much into how many people would actually be willing to wait. And then there's the service discipline. And these are configurations on how do you prioritize the order of how you're going to be providing the service. And this is a lot of times used in manufacturing or even in food industry, because we would have policies show like first come, first served would be the most common, okay? But it's that is not always the case. In manufacturing, especially when you have big items in storage, traditionally the thing that you would do is the last item that you stored is going to be the first item that you're going to retrieve, depending on the configuration of the storage as well. So in a lot of places what they're trying to do, and that's one of the lean things that Toyota does it very well, they try to design these storage devices that keep the policy of the first come, first served. Very simple. How do you feed the refrigerators at the supermarket? From the back, so that the items that have the sooner expiration date are always at the front, right? So you feed from the back. If it's a smaller store that doesn't have that configuration, what happens? You feed from front. So always you push and push and push, so the item with the sooner expiration date would be always at the end. So there's all these sort of characteristics, but I guess what we're going to try to do is first understand the parameters of how queuing theory is explained, and then I guess the time is going to just allow us to explain the most simple configuration of queuing theory. So to understand this, this is how we are going to view queues always. And this is the common notation, is called the Kendall's notation, where we're going to find these things. If you Google these things, you're going to find theories about different queues and different characteristics. And there's a lot of papers and studies for very specific configurations of queues. So the configurations are going to mean the following. And if you like to use simulation at some point, this is the information you need to feed in order to create the simulation model. So we're going to have A. A is explaining what is the type of arrival process. So the type of arrival process and service process is B are going to be determined by any of these three parameters. Okay? So the first parameter is the queue is behaving in a Markovian process. What that means is exponential arrivals. Okay? It follows an exponential distribution. And this is very good because if it follows this, it's simpler to explain. Okay? So exponential distribution is just the rate of arrivals follows the inverse of the from basic probability, the Poisson, I say Poisson or Poisson distribution. where you just measure the average time when you arrive, okay? Then we have characteristic of G, which is completely general distribution, right? Or deterministic. There can be deterministic distribution in many cases. This is very easy to model, but is more unlikely to happen in real life. So the most widely used parameter is Markovian, or exponential distribution. Okay? So we're going to use any of these three for here and here. Okay? So that's arrival and service. Arrival, this part right here, the time, it will be always kind of an average that you're going to get. And then service time, again, will always be kind of an average. Okay? The averages you're going to get here and here is going to be per unit. So average time of arrival is per unit. Average time of service is going to be per unit. Okay? Then we have M. M, in here, in factory physics, it's the number of machines. But traditionally, queuing theory is going to be the number of servers. So that basically goes 1 server, 2 servers, 3 servers. And that's as simple as, if we take the movie theater example, the windows open. Okay? If we go to the Walmart, is the number of registers open. Okay? So that's the number of servers. And B is less likely to appear because when you model these type of things, traditionally it's very difficult to find a line that grows beyond certain capacity. You will always focus on modeling this part right here, but if it is an important parameter to measure, then you would add this as the capacity of the system. Okay? So that's basically how many, the capacity of the system will be determined. You get this one plus how many can be here in any given time. Right? So these are all sorts of notations that we're going to be using. We already covered a few of these. Rate of arrivals, same thing as we covered. Then the average time between arrivals, same thing, the inverse. Coefficient of variation, then the M, which is number of servers, in this case, number of machines. We have a new parameter here, which is the buffer size, basically the B that we had at the end. And then these parameters here that explain the process. Same thing, right? Processing time, then rate of processing time, which is the inverse, and we can use the M, number of machines, and then coefficient of variation. And then the last concept that we introduced, which is the utilization. Okay? So, this is what we're going to be measuring. Just kind of a suggestion, if you can draw in your notes that figure that had the big A and the B, the Q and the process, I would put some of these notations on top of where they belong, either on the left or on the right or overall. So the CTQ is basically the, can I say, the cycle time of the queue, if you wanna, if it makes it easier to remember. So that's basically how much time you're gonna have an average waiting in that particular queue, or that particular line. So that corresponds to the left side. Okay? just the Q. CT would be overall. Time spent at the Q plus time spent being served. Okay? First one only belongs to left, to Q. Second one is the whole thing. And then whip without no index is basically jobs at the particular station, and then whip sub Q is number of jobs on the left side. Okay? So again, this is the whole thing. This is just on the left. Is that okay? So, what was the golden rule that we had from pretty much class 3, I think, lecture 3? What was?
Reduce lead time.
No, that's the principle. The law. Give you a hint. Law. Little's law. So with Little's law, if we remember, we can bring back that to these principles and we can explain the behavior of that particular queue. So again, the waiting time at that particular station, the overall thing, equals the, well, that's the explanation of how this is conformed. But then the relationship of whip here is equal to rate of arrivals time. What is this? Overall cycle time, right? So we're understanding the parameters that we have before from the perspective of queuing theory by using or remembering the relationships in Little's law. Equally, if we want to get the inventory at any given time of the queue, we just change the rate of arrivals by that number there, that is the cycle time at the queue, okay? Or the waiting time, if you want to go from. So what is RA? What was in Little's law, RA?
Rate of arrivals.
Here is rate of arrivals, but what was in the initial formula that we had? Throughput. Okay? So we have a new name for throughput now. Throughput is rate of arrivals from the perspective of queuing theory. Okay? So if we know the waiting time, then we can calculate all the other stuff. Why? Because we have this one, and we have this one, so then we can just populate up. Okay? So that's the importance of measuring waiting times. Okay? Now, how do we do this in reality? Measuring waiting times? I think the best way to do it is using video and with a computer. There's many softwares now that help you just to bring in the video and start analyzing the parameters of the video. Okay? If you try to do it by yourselves with a stopwatch or something, you would need help, or at least two or three people, because you have to measure. Somebody has to focus on inter-arrival times. Somebody would have to focus on how long a person was waiting in a line, and somebody would have to focus on when people departed. So it becomes very complicated to do that just by observation. The best thing is to take video. Or you can design systems where, I don't know, you get a ticket, scanning the ticket, and just going back to analyze that data, it will tell you immediately all the things. How long, when did they arrive, how long they waited, when they were processed, and then when they moved on. So that's where Kanban cards, if they're well designed, help to analyze this whole thing, the queuing theory. So are we good with these parameters? Because there's a bunch more formulas that are common. All right. So according to Kendall notation, the most common model in queuing theory is known as MM1. What does that mean? We said the first two parameters meant what? The first one is arrivals, right? So the arrivals behave in what way? Exponential. Markovian process or exponential, all right? Then the second explained what? Process. So the process is same, exponential or Markovian. And the third, it has a 1. What does that mean? What does that 1 mean? What was that? Capacity?
Not over.
Either M or B, little M or little b, but
Yeah, there's no B here.
no B. All right.
No
So
B.
it's Number of machines.
Number of machines or number of servers. So this is the most common model. There's tons of research developed around this model. MM1, which is exponential arrivals, exponential service, 1 server. Okay? Why is this the most common? Because that's pretty much what you will find in most cases. All right? If you go to a store, a gas station, most likely there's going to be only 1 register up. There's somebody helping in the back. If the line starts to grow, then the policy changes. There's another person that comes to help. That would change the model to 2. But again, how can you predict when a person is arriving to a gas station? There's only certain parameters you have, but it's pretty much exponential, right? So this would be the most common model. If we take this model, okay, these formulas apply. When we change the parameter of the model, then a lot of these formulas would change, okay? So we're gonna take this, because if we take a production line, what we were seeing earlier, there's 1 queue behind every process, right? When we connect all the processes in series, then we have multiple of this same model, right? So that's why it's pretty much the way to explain most of the factory physics problems. So how do we calculate inventory in an MM1 model? The calculation of inventory is just the ratio of U. What was U? So it's a ratio of the utilization of the process, and the utilization goes from 0 to 1 divided by the idle time. Okay? So that ratio explains width. The cycle time, or the waiting time, sorry, the time from queue to process, the whole thing. The relationship is explained by, if we took take the little slow formulas, we have divided by throughput, or we said that we were going to rename it here as rate of arrivals. So it's width divided by rate of arrivals, which equals what?
Process.
Processing time divided by the idle time, right? Now, I'm not going to call it idle time because it might create the confusion, but it's the reminder of the utilization. Then the time in queue, or the waiting time, is going to be the subtraction of the total time minus the time that it was in the process, right? So this equals same thing times, which is the u divided by 1 minus u times the processing time. Okay, average processing time. So the last one is the inventory in the queue. So that's basically relationship between rate of arrivals times the cycle time of the queue. Does this make sense? We're just taking the formula. So these are very important because these are the things we're going to measure from the queue. We're going to measure inventory in the inventory waiting, okay? Then inventory overall, processing time, waiting time, and the overall time. All right? Okay, so here's an example. I don't know if Dr. Sonny went through this example before. There's two processes. One is called the tortoise and the hare, yeah. So we're gonna use the same parameters so that we can compare how this works. So we have the rate of arrivals here at 2.875 from same information that was used before.
Yes.
And this is the processing time. It's 20 minutes or 1/3 of an hour. And then the coefficient of variation, okay, of the process is 1. Just as an assumption, we will use this for this particular example, okay, so that it proves a point. So we're going to calculate WIP, and the WIP is what? Just the utilization time that was given over here. Let's get that first. Rate of arrivals and the rate of processing, so it's 2.875, and you can do 3 jobs in an hour, right? Does that make sense? So the utilization is 95%. So we just take that, 95%, and 1 minus 95. That's roughly 23 jobs, okay? So any given time in that process, we're gonna find 23 jobs overall. So the cycle time is just 23 divided by the throughput, or the arrivals, rate of arrivals, 2.87. That gives 8 hours, okay, which is the whole shift. The cycle time of the queue is just 8 hours minus 0.33, so it's 7.6 hours, which is fairly long, okay? And then the WIP of the queue, you see? So what to look for in this? This is a logical relationship. If you have long waiting times, what is the most likely thing that you're gonna have? A very large queue, right? If you have short waiting times, you're gonna have a very short queue, okay? So this is this one. The other model that we will explain, the GG1. What would the G mean? General. Okay? So when we have these parameters, when we have general distribution, the whole game changes. The waiting time in the queue is going to be determined by coefficient of variation of arrivals and coefficient of variation of the process times, what was that? What was U divided 1 minus U? Was WIP. Okay. Times processing time of the station. Okay? So, the whole point of this is basically that we introduce both parameters into the equation, which means that the variability causes congestion because waiting time increases if the coefficient of variations are higher. Okay? So all you gotta add to that is this element right here from the exponential model, or from the Markovian model. Okay? All right, so let's compare both. So we had all those parameters. And which one we had? We had the Ordos, okay? So these are all the information we get to, where is this? This one, okay? We got that already. And this here, we have the coefficient of variation squared, 6.25, so let's just compare. So if we check only those red numbers, the processing times are exactly the same. Coefficient of variation for the hair is much higher. Coefficient of variation for the tortoise is smaller. So what's going to happen with that? When we compare, why are we comparing instead of MM1 with the tortoise with the hair? What was the characteristic of the hair machine?
Long
Had
downtime.
more, it had more frequent, but less outages, had more of their.
Less outages, more frequent. Okay? And the tortoise was?
Less outages, yeah,
Yeah.
less outages, but longer.
I think you got it backwards.
Opposite.
Then the tortoise, like, or the hare, have longer outages but less frequently.
Right.
Oh, I've heard that.
Did I say it backwards?
I think it's, I don't know, I heard it backwards.
My bad.
That's all right.
So, MM1 explains the tortoise. GG1 explains the hair. Okay? So let's calculate all these things using the same parameter. If we were to use the arrivals at 1, exponentially distributed. So what we gotta do is we add the component of this for the general model. Okay? So that was coefficient squared of arrivals plus coefficient squared of the processing time divided by 2 times the utilization rate that we had, which is the WIP, times the processing time, which was 20 minutes, right? So that gives you that in minutes, which is 27.79 hours. So what does that mean? If we compare it against this one, what is the configuration that you would prefer to prevent standing in line? So what happens in one scenario, what happens in the other. So the whole point of this is basically that you visualize that certain effects or certain parameters of disruptions, how they are quickly fixed, how predictable can we have a machine failing and getting it back on track, versus I don't know what's going to happen but when it happens, it's very, very bad, creates in the overall system. Okay, so all of this is magnifying that variation as how it should be, so that this creates a good policy for what you decide to do. You know what things you can control and what things you cannot, right? Behind the things that you can control, you may decide, okay, what's better for me? What do I have time for? What do I want to do? Do I want to approach it where I make sure things don't happen, but if something happens, I don't really know? Or do I want to get something that is more controllable? I mean, that is pretty obvious answer, I guess. So let's make the relationship that we were talking about. Let's assume that these two machines are connected in the process, so that now we want to understand that relationship we explained before, which is low variation of arrivals, high variation of arrivals, so on and so forth. Okay? So this is the hair, okay? And this is the tortoise. Okay? So one is going to feed the other. We said that whatever was the departure rate or the arrival rate, coefficients, and everything was going to create that link between the two processes, right? So that means that the coefficient of departure squared of the hair equals the coefficient of arrival of the tortoise, right? Which was what? 5.82. So the Q between this and this is 26 hours, right? If we just have this from the perspective of the hair, the Q behind the hair is, what is it? Lost it. 27 hours. So what's determining the Q at the tortoise? What is determining the Q there? Let's see what's the Q at the tortoise originally. The Q at the tortoise was 7.6, right? The Q of the hair is what? 27. If hair was to feed the tortoise, it goes from 7 to? So what's determining this change? The arrival rates of the hair, right? So what's the phenomenon that we're seeing here? Let's go back to that.
Well, the hair puts out a lot of stuff and then it doesn't for a long time, right? Basically, because you're down for a period of time.
What is determining what? we are analyzing the Q between the tortoise and the hare, right? So this machine right here would have to be the hare, right? So we are analyzing what's happening here through understanding this and this. Is the hare high utilization or low utilization? It was high utilization, right? It was 95 what we had. So this one explains it. What's happening here? Which one is explaining the Q of the hare? And which one of these is the hare? Here?
All right, one up. Top one, maybe?
This? Third?
For the tortoise?
For the hare. Which one would be the hare?
Second be the one.
First one.
First. Because it's more frequent.
It had low variability on arrival.
Low variability on arrivals,
High variability.
high variability in the machine. So then, what is the problem? If you were to reduce the waiting time between those two machines, where should you focus?
Process time for the hair.
Right here.
There you go.
All right? So, this is the whole thing, the whole idea. The numbers, you can always get them from the book, the formulas and everything, but it's how these connect to each other. Where should your attention be put to? What time is it? Oh, it's about time, right? Okay, so we left that. Yeah, right here. Yeah, that's okay. So we can stop right here.